So welcome back, everyone. So we're starting today. So we're talking about classification, and so the goal of the lecture today is just to find, so what is the classification problem? What is a linear classifier? And make sure that's on mute. Okay, so we're starting today. All right, always okay. So with classifiers, there's going to be kind of, this is the last kind of section we're having in this. So in this course for the semester, the reason we have them at the end is so a few reasons. One, I would say maybe the math here is a bit more complicated than some of the other things we did. But since we've seen a bunch of other stuff throughout the semester, hopefully it's not as hard. We'll see linear functions, and these should be easy at this point. And we'll go beyond linear functions like we did with regression, but it's going to be kind of slightly more general how we do in the setting. And we'll look at other things that go beyond just these linear classifiers as well. We'll build on various techniques from gradient descent to kind of thinking about high dimensional data. So we'll kind of do this. And so that's one of the reasons at the end, this is the end of the semester. I know there's been a lot sort of going on this semester, and in general, usually people are kind of tired at the end of the semester. This is probably the most, this linear classification is about what people do in machine learning. It's probably one of the most powerful tools we'll talk about in this course. And so I hope you stay engaged, even though it's the end of the semester. We'll try and make the assignment and the quiz in this topic a little bit easier because we're towards the end. You'll still be tested on it, and I hope you'll still kind of pick up all the information, but kind of hopefully your interest can help carry you through as we finish this off. I think the material's kind of very cool if you haven't seen it before, definitely. So let's just quickly look at the schedule. Boy, we've covered a lot of material so far. I think it's been pretty cool, all the way from kind of basic probability and linear algebra and kind of how to think about data analysis in a probabilistic way, think about data as vectors and matrices, to linear regression, gradient descent, which we'll see again in this section, dimensionality reduction, clustering. We're finally at classification, right? So last section of the course, maybe 4 lectures here, and then we'll have a review sometime. I ended up having a PhD proposal that I need to be on that partially overlaps with when we would have had class on that day, so I'll probably shift it back a little bit. But on the review session after the end of the semester. But we'll plan to do that after these last 4 lectures. So what is left? You guys have finished 5 quizzes. So right before the lecture, sounds like Hassan just posted all of the grades for quiz 5. Scores were a little bit lower than we'd seen, not too much lower, but slightly lower. And then a number of people got lower. Not everyone turned in the cheat sheet as much this time. So I recommend doing that. That's free, 5 points if you missed them. Quiz 6 will be coming up in 1 week, right? It'll be on clustering and this lecture and next lecture as well. That'll be next week. And then you guys finished homework 4. That was, I'm pretty sure, was probably the hardest homework of the semester. You did some kind of pretty advanced stuff in homework 4, and I'm kind of glad everyone was able to get through it. I think you really understand, if you can do that, you really understand the core of what's going on and how most models are built over data. So that's great. Quiz homework 5 is now posted. So we posted that around last Friday or Saturday. I quietly posted it, but it's should be up there now. This will have no, it does not require any Python. The first question you might decide to answer this with Python, but it's not needed. So the first one's going to be about clustering, both the kind of the assignment-based clustering for k-means, as well as the kind of mixture of Gaussian things. You don't actually have to run the full clustering algorithm, but you're going to kind of run the core part. And then there, to run the rest, you're doing like there's a for loop that wraps around here where you iterate, and a bunch of cases that I mentioned. So we're going to skip that part, but you're going to kind of make sure you understand this underlying distance function, which is driving it. Question 2 is also about clustering. And so those you should be able to get started on now. The last 2 questions are going to be on classification, and you may need the next few lectures to answer those. Probably the next 2 lectures are going to be enough, but we'll see. At least, if not, the next 3 should be enough. Okay, so that's linked off of here. And this is due, I put it due at the end of Friday next week. So that's after the semester ends. It's at midnight on that Friday night. I've heard students like stuff due around midnight. If this deadline becomes problematic for something else, you can kind of let me know. I'd like to get it graded before your final exam, though. So that's the reason for a due date around then. Okay. The first lecture will be defining the problem. And we'll talk a little bit about algorithms today. And then the second lecture on the perceptron algorithm is, like each of these sections, we've kind of had one devoted to a very basic algorithm in here. And we're going to talk about a very cool and simple algorithm in this case. And then the third and the fourth lectures on kernels and SVMs and neural nets are going to kind of be about extensions and kind of a preview of some of the kind of much more interesting stuff that's going on in a machine learning class, right? So we're not going to cover all of machine learning in this course. We have 4 lectures to do it, but you're going to kind of get a pretty good sense of what's going on here. All right, so any questions on the remainder of the schedule for this semester? So great. So let's go into this lecture. Great. So linear classifiers. Okay. So the input here is going to be X subset of R n cross, or that's an element of R n cross D. Actually, let me write it as a subset of RD. Subset of RD, this is typically how you think about it. You have points, X is equal to X1, X2, up to Xn, right? Each of these is an element of RD, a d-dimensional point. But you also have these labels. This is a supervised problem, so like regression. Although now the labels are not going to be in R, they're not going to be real values. The labels is going to be an element. Yeah, it should be a subset here, subset of RD. But these labels are going to be, okay, these are going to be elements of -1 or +1. Okay, sometimes this is written as it could be 0 or 1, right? But it's going to be a binary set. There's going to be 2 classes here. Okay, so each yi is going to be either going to be -1 or is going to be +1 here. Okay, there are 2 classes. Okay, and right, and so the goal is to build a function that's going to be able to predict these classes from this data. Okay, so the goal is going to be a function g, which is going to go from RD and going to And actually, it's going to go to -1 or 1, but it's a lot easier to work with these continuous functions. Okay, so we're going to map it to the real number. So it's like a regression problem this way. But so if xi, yi has y equals to +1, then we want g of xi to be greater than 0. Otherwise, we want g of xi to be less than 0. Okay, so we're typically going to build this function, and we want to predict if the label associated with an x value is going to be positive, then we want our g function to be so positive, and if that label associated with the x function is negative, then we want is -1, then we want the g function to be so negative. It can be -742. That's fine as long as it's negative, right? So think of, we've got some sort of domain, right? This is our D, but I'm just going to draw one dimension, and this is going to be R, and there's going to be some sort of function, right? So this would be a function G, okay? And we want to say, well, if we have a data point xi, we're going to look at the function value, okay? And this is, and so if you look at this x-axis, this is greater than 0, and this is less than 0 down here, right? So you could think of the positive points as being, right? So these points is where g is greater than 0, and we predict any of the x values in here as being positive, and then any of the x values in these pink regions as being so negative, right? So this would be, predicted to be -1, and these functions as +1, +1, +1, right? So there's some function, we're going to learn this green function somehow, right? And based on the x values we have, we want to predict whether it's going to be positive or negative. We could just predict this binary class. It turns out it's going to be easier to optimize over a function where we can then just kind of look at the sign of that function. Okay, how do we define points that lie in the x-intercept? Yeah, so we could either predict those either way. We're going to have some uncertainty on those points, right? So if you do have some points which are kind of right here, right on this boundary, these points are probably going to be pretty rare, right? Think of this as a continuous function in a probabilistic sense. These points are so if the points are drawn from x, these points are going to be like a measure 0 or something like that. In those cases, we could classify them either way. We're probably not going to have a lot of certainty on those points. So I think one of your homework questions is basically going to ask you, what happens if you have this uncertainty zone and you want to kind of score those as kind of halfway in between kind of +1 and -1 or something kind of like that. How can you do that? Yeah, so these are kind of, it turns out not to be so important in most cases. If it was more than a handful of points, then you're not going to have it. And we'll actually optimize so that we'll learn these functions g, and we will kind of, if we know what the label is on the function, right, then we're going to force what the label is on that data point, we're going to force it to be the other way. Now, if we're trying to generalize to new data points and we get a point that happens to be right in the boundary, well then, we can kind of guess, right? So it's an interesting kind of, it's a good question, but yeah. So I'll say kind of, the thing we're going to start with today and for the next lecture as well is we're going to enforce that G is so linear. Okay, so it's going to be a linear function, and we'll talk about that's going to enforce a lot of structure onto what we're doing and kind of and make a lot of stuff work. And through the next 3 lectures, all the same structure is going to be there. Even if it's not linear, we're going to be able to use all the same machinery anyways without restricting to these linear functions. And then we'll talk about completely different stuff in the last lecture. Yeah, so I guess I didn't say too much on motivating why classification is kind of important, kind of as opposed to regression, right? So like if you're a sports team, right? So if you're the youth football team, the final record of the team does not matter whether they lost by 1 point or they lost by 20 points, unfortunately, but it just matters if they won or they lost, right? So we're just trying to predict this binary outcome, not necessarily the score of the loss function. It turns out in predicting how well future teams will do, kind of factoring the score is important. But if you're just trying to care the win-loss column, you're advancing in a tournament, you just care who wins and so who loses, right? So with politics, right? There's a winner and there's a loser of an election. Even a couple of years ago, there was an election in, I think, Virginia in some place where there was a tie. And they had a tie-breaking rule where they literally flipped a coin or they drew a straw or something, and one person won, one person lost. There wasn't the margin of votes doesn't matter so much as who wins and who loses, right? So is someone going to, if you're trying to create a movie, is someone going to buy the movie or watch a movie or pay a ticket for a movie, or are they not going to do it? There's some binary outcome. Are you going to click on an ad on a website, or are you not going to click on an ad? There's this saying that kind of a lot of the best minds in our generation have been working on trying to get people to figure out which ads people will click on websites. If you don't know, most of the profits from Google and Facebook are derived from the ads that they display on various pages. And they've gotten very good at figuring out which ads people will click at. And that's part of the reason why they've become so profitable. They're also having products that are engaging without saying anything more than that. Yeah, and so are you going to get a job or are you not going to get a job, right? You can build a good classifier, chance you probably can get a pretty good job. As it turns out, this is a thing in hot demand right now. Great. So classification is kind of a pretty important topic, right? Okay, so let's go on. So what is a linear classifier? So I want to find this function g, and I want this function to be linear. Okay. So remember, we're going to have a linear function g from RD to R, okay? And that's going to mean we're going to have a function of x. And now I'll say that x, which is an element of RD, I'll drop the subscript of x, and I'll say that just because we have subscripts and we also have the coordinates of x, so I'll say the coordinates are x2 up to xd. Okay, just to, I don't know, the notation here is a bit clunky, but we'll do this to try and be consistencies between which data point it is and the coordinate, and I'll put the superscripts for in parentheses for the coordinates. Okay, so this g of x function, okay, this is going to be, it's going to have a special form, right? We've seen linear functions before. Those can have to be parameterized by some sort of alpha vector. right? So it's going to be plus alpha 1, first coordinate, plus alpha 2, the second coordinate, plus alpha d, the dth coordinate, right? So we'll often see this as, and we can write this as a dot product, or we can write this as j equals 1 to d of alpha j x, the jth coordinate, okay? And so then our model is going to be this alpha vector. We can parameterize it by alpha, which is alpha 0 up to alpha d, okay? It turns out, so within so dimensional reduction and in regression, it was probably better to turn this model into an element here. This is an RD plus 1, and then to just work with this alpha vector. For classification, it turns out it's different, and it's better to keep the offset around separate. Okay, it's a little bit more natural to work that way, and the distinction can come up in a few places. It's just going to be easier to work with, and so we're going to write this as B, where B is going to be the offset, and then we'll write this as J equals 1 to D of Wj xj, right? So the model is going to be BW, which is B, and then W, where W is going to be in RD. Okay, and so this is equivalent to this dot product between W and X plus some offset here. Okay, and so it's going to be easier to intuitively think about these as different quantities and explicitly think about what this offset is doing. So this guy is, right, so this B, this is going to be the offset, right? Like we had this constant term in sort of regression. Now this is going to be the distance from the origin 0, the all zeros vector, to the classifier. Okay, and then this other term, this W, we're going to this is going to be the normal of the classifier, and we're going to make this a unit vector. Okay, so this model, we can think of this as the kind of the offset, the distance from the origin, and the unit vector. Okay, so I think at this point should draw a picture here. Okay, so our input, let's see. So we're going to have, makes sense to draw the axes. Okay, and this is now going to be RD. Okay, so I'm not drawing RD on the x-axis and then one dimension for the y-axis. This is the d-dimensional case. In this case, d is equal to 2, right? So d is equal to 2. So this is the origin, which is the all zeros vector. Okay, and then we're going to have some data points in RD, and we're going to have two types of these data points. Okay, we're going to have the positive data points. These are the plus ones. Okay, there's the plus ones of the data points. There's the minus ones of the data points. Okay, there are only two types, so I'll draw them in two colors, and I'll draw so that let's make this a little, other aspects a little bit easier here. Yeah, and so there are, okay, so there are two colors, and one has a plus symbol, one has a minus symbol, okay? And we want to build now a function, a linear function, which can classify these points well. Okay, and we'll try and find a function that's going to look, yeah, so our function g might look like this. Well, this will be the boundary of the function, right? We want this to be where, this is where g of x equals 0. This is the line where g of x equals 0 right here, right? And this is over here. This region is where g of x is greater than 0. And let's say this region over here is where g of x is less than 0, right? So there are these two regions, and on one side it's greater than 0, the other side it's less than 0. Okay, and it's a linear function, and so the points where it is exactly 0 has to be a line in this linear function. And partially, how do we see this? Okay, well, we're going to define some normal vector. This will be w, the normal vector. So it's normal, so that means that it's perpendicular to this line. All right, it's a vector in RD, and it's a unit vector. Technically, it's a vector from the origin, but you could think of drawing it on this point. And then the value b is this distance. B is the distance from the closest point on the origin, right? So we're doing like a linear projection onto the from the origin onto this line, and we look at that difference. You could think of that as b, right? So if I right, so this is what this picture looks like. This is for a function g of x equals the dot product of x times w plus b. Okay, so let's kind of walk through an example with one of these data points here. All right, so let's say that I'm going to have a data point that is going, let's look at, say, this data point right here. Let's call this, let's label this guy x1. Okay, so I'm going to take a dot product with w, right? So I take a dot product with w. Well, w is the normal vector here, right? So I take a dot product with it, and my distance is going to be negative. So maybe this is going to be negative 1.2 is the length here. Let me put this down here. Negative 1.2 is the length backwards that this point is going in this direction w. Oh, but I want g of x to be positive on this side of the line. Well, I'm going to add b, right? So let's say b is equal to a length of 2. So I'm adding b to it, right? So anything that is that the dot with w is greater or equal than negative 2 is going to get a positive value, right? So g of x here, g of x1 is going to be the dot of w with x1 plus b, which is going to be equal to negative 1.2 plus 2.0, which is going to be 0.8, which is greater than 0, so it's positive, right? So this is how we define anything on this side of this line. The direction that w is pointing is going to be positive. Anything that's going to be on the other side, it has to be negative, right? If we look at instead, say, this point over here, let's call this guy x2. G of x2 is probably going to be the dot w of x2 plus b. This is going to be something like minus 2.9 plus 2.0 is going to be equal to negative 0.9, and this is going to be less than 0. Right? So if I look at that point, it's on the other side of the line. It's too much for this offset b to recover. B could also be a negative value, and then it shifts the green line on the other side of the origin, right? or W could be pointing the other direction. And but I can get any sort of, using this normal and offset, I can basically draw any sort of line here. Okay. And draw any sort of linear separator. Okay. And this allows, even though, think of this as a function that's cutting through the plane, it's coming up out of your screen, right? So it's coming out of your screen, and it's coming above the screen, so it's positive on the side where all the plus points are, and it slices down through the screen negative on where all the negative points are. If the offset was 0, it would cut through right at the origin, and basically W would tell me the direction that it was going upwards. But then when I have this offset, I get to basically add 2 coming out of the screen, and so that shifts where this boundary is. Okay, so they're hopefully helped kind of give you a picture of what this function is doing. We're learning this linear function, and then we use whether it's greater or less than 0 to determine what the prediction for the sign of the point is. Okay. So great. So hopefully this idea of linear classification, kind of building a linear function and using that to predict classification, is going to kind of make sense. Okay. For any questions about that now, we can spend more time, but I want to think a little bit about how do we find W and B, right? So how do we define this model, this model G sub W and B, which defines it? How do we find this model that gives us this sort of so good prediction? All right, so we have a couple of techniques we've talked about so far, and that we can solve very similar problems. And so I'm going to start by kind of walking through these approaches and show that they don't quite work, right? Okay, so the first one is by, say, linear regression. Okay, where what I can do is I can so I can basically turn my data set X, which is going to be an element of R n cross D, into X tilde, which is the element of R n cross D plus 1, where X tilde I is equal to 1 xi, right? So I've added this one offset, right? So I've kind of I've added a column that allows me to learn for this offset using this alpha trick, right? And so then I can say that BW is equal to alpha in our D plus 1. Okay. And then my model, right, is going to be G of alpha of X equals alpha 1 X, right? So this is kind of the formulation we've seen before. And then we can solve with alpha is alpha star in some sense, some sort of optimal alpha. It's going to be X tilde transpose, X tilde inverse, X tilde transpose, and then Y. Remember, Y is a vector, right? It's an n-dimensional vector, and we have a value, a -1 or +1. And so this is how we would solve for like linear regression, right? I can solve for this value alpha. So exactly, it's optimal in some sum of squares sense, right? So what this is trying to do, this is so optimizing So that G, so the sum of I equals 1 to n of G of alpha of xi minus yi squared is small, right? So is optimizing, or yeah, so actually, so minimizing, right? So this sum of squared errors, right? So okay, so you know, there are some cases, a lot of like so neural nets actually in their optimization function, they actually use this, even though it's kind of strange. It ends up working okay for various reasons, but it's I would say it's not the typical thing. It's some things work with neural nets for strange reasons we don't quite understand yet, and I'll maybe give some insight to them in the last lecture. But this is not the typical way you would solve it. And let me try and show this by an example of what's going on. Okay, this is kind of a strange way to solve it because we want to think about, so we have now, this is now going to be RD, and this is going to be R, right? So think of our data, if we want to draw it, think of it this way. We're trying to solve a regression problem. Okay, and so what that means is that we're going to have this point +1, and so -1, and you're going to have a bunch of these points which are kind of have the pluses up here, and then you can have other points which are going to have the minuses down, all have these values. Okay, so it's going to be something like this. They have to either be on, let's say, they have to either be on this line down here or on this line up here, right? So these are the only two cases. And now we need to, and what we have to fit a model through here. And we're going to fit a model. What we'll end up doing is fitting a model that might look something like this. Okay, and what that's trying to do is it's trying to look at these, so it's trying to look at these, so residuals. So this would be our function G that we get from alpha star that's optimal under this least squares. That's looking at these residuals, and it's trying to minimize the sum of their squared errors, right? So it's trying to minimize the sum of the squared lengths of these green lines. Okay. But if I look at how this corresponds with a classifier, if you know, it may have misclassified this point here, right? If I look at this this point here, let's call this x3, right? X3 is going to be equal to let's say +2, right? So and it's going to have, you're going to have y3 equals +1. Okay, but it's going to be just on the wrong side of this classifier, and that the function value can have g of x3 might end up being minus 0.01 something. It's negative. Okay, it said this point. You know, my goal was to minimize the sum of the squared errors. So I made this point negative. You know, it doesn't matter if it's minus 0.01 or plus 0.01. That doesn't change the sum of squared errors very much, but it completely changes the sign of this prediction at this point. Okay, so linear classification is, because of a couple of points over here way on the side, it's kind of, well, I want to make this classifier a bit higher, and so I'm going to misclassify some points. Maybe I didn't do this right, but if anything, I feel like I should have made a classifier higher and maybe missed a couple of other points. But so it's not quite the right cost function here. Okay, so and actually it's saying if I were to make this classifier up here, then so basically if we increase, you know, g of x, so if I increase the offset, right, then these errors are going to get even worse. I'm going to get more error over here. Then I'm going to get more error over on these points, kind of over here, right? These points are going to get more error if I increase the classifier. But I had these classified correctly, right? They were classified the right way, but if I made the error more, so if I move them further left, this classifier is going to want to be lower, and it's going to do a kind of a worse job of classifying the points close to the boundary here. Okay, so this is not quite the right cost function. These points over here, and kind of the same thing is going to happen kind of in the opposite direction with these points over here. These are penalized for being classified too well, right? Again, these are penalized for being classified too well, right? So it's kind of a little bit unintuitive, right? The cost function, as I classify things really well, it starts to penalize points more and more. Okay, so it's not quite the right cost function here. Okay. Okay, so how do I want to make this cost function, right? So so I'll call this the delta cost function. This is an uppercase delta, right? In LaTeX, this is uppercase delta, right? It's a kind of a triangle. And so I'm going to look at this delta cost function. And so we're not going to use, we're not going to use sum of squared errors for this section. So that's another reason I put it towards the end, because everything up until now we said sum of squared errors basically gives you the right thing that's going on. And in this case, it's not quite, you know, it's, some people use sum of squared errors probably out of habit, but there are better ways of defining the cost function. Okay, so we're going to find this delta cost function. Okay, and this will take in a function g alpha, right? And it's going to take in a data set xy. Okay, and so this is going to be, again, the sum 1 to n. So it's going to be decomposable. I'm going to sum over each of the elements in my data set, each of the data points. And it's going to look like this. So it's going to be 1 minus, and it's going to be this function, so which I'm going to call the identity function, and I'll say what, I'll kind of write this and I'll explain more carefully what this is if you haven't heard of an identity function before. But it's going to compare the sine of yi, check whether that's equal to the sine of g alpha of xi. Okay, it's 1 minus that. Okay, so here this this is called the this symbol. It's kind of like a blackboard bold 1. Okay, so we'll call this the identity function. Okay, and this is defined. So it's going to have a truth inequality inside of here, where if inside is equal to true, then it's going to give a value 1. If the inside here is false, it's going to give a value of 0. Okay, so it's kind of taking a true-false expression and turning it into a binary thing. You know, in some programming languages, these are kind of equivalent to each other, right? Sometimes a true can be mapped to 1, but kind of think of turning a binary, a true-false expression into something that's actually 0, 1. Okay, so that means that if the signs match, so if sine of yi is equal to the sine of g alpha of xi, right, that my prediction made the right sign prediction. I gave +1 when it should be a positive value, when it should be +1. Then I'm going to get a 1 and 1 minus that. So it's going to have a 0 cost. Okay. And so, and if it's the, and if it did mismatch, I predicted -1 when it was +1, or it was -1 and I predicted +1, then the identity function is 0, and I do 1 minus 0, I get a cost of 1. Okay, so this is ultimately going to be the number of misclassified points. Okay, so it's the number of misclassified points. I'm counting how many points I've misclassified. All right, and so this function, this is what we'd like to minimize. We'd like to minimize the number of misclassified points, right? We'd like to minimize this cost. Yeah, so this is kind of, okay, so if I look at this function, I want to minimize the function, and I still have some parameters alpha, right? These parameters alpha govern whether it's misclassified or not. Could I run gradient descent on this? So can I solve with gradient descent? Right, so answer in the chat, kind of who thinks I can solve this with gradient descent, right? Is this what I'm going to do next? I'm going to show you how to solve this with gradient descent, or am I not going to be able to? Okay, I see someone used a check mark to yes, use gradient descent. So great. You can also do that in the participants window. So who thinks yes in the participants window? Hit the green button. Who thinks no? Okay, I have 3 votes. There are like 30 some of you out there. Let's get those votes up. Okay. I'm not going to keep track of who voted for what. Let's see some votes. So at least get to halfway. We're almost there. Okay. All right, it's pretty close. Right now we've got 12 no's and 8 yeses. Okay, so it's okay. So the answer is going to be so no, we can't do gradient descent. There are 2 reasons why we can't do gradient descent. In fact, so this is going to have the first reason, and this turns out is not the major reason, but we'll pretend it is. It's going to be not so convex. So it's not convex. So if we run it, it might not converge properly. Turns out most deep nets aren't convex, and people still do it anyways. But the bigger reason is there is no gradient. So there's no gradient. We can't define the gradient anywhere for this function, right? There are points where it changes. If I cross over, if I look at a classifier, right, and I cross over a point, the sign changes. But if I move it a little bit, it doesn't change very much. If I move this green line just a little bit here, I'm going to classify correctly or incorrectly the same number of points. So my cost function doesn't change. And then at some point, one point's going to cross over, but that's going to be a discontinuity. It's going to be discontinuous. So I'm not going to have a gradient even at the points right on the boundary. Okay, so it's going to have not convex, and it's not going to even have a gradient, which is the biggest issue. Okay, so I'm going to kind of What people typically do, we are going to run gradient descent, okay? But we're not going to quite solve this function. We're not going to solve this delta function. This one's going to be too hard. We're going to have to do a proxy for it. Okay, so instead, we're going to find a proxy for this function. We're going to find something that looks kind of like it, and we'll solve that instead. Okay, so it's a little bit unsatisfying because we're not solving the true function. It turns out that's hard. The good news is on Wednesday, we are going to solve this function with a different algorithm that can't always work, but it can sometimes work. And then there's a different algorithm we can solve for this delta. Okay, but we'll see that on Wednesday. But that algorithm can't always work. We're going to first see something that's more general. That will always work, but it will solve a proxy. Okay, so we're going to use something we're going to call a loss function. Okay, and this is going to be a proxy for delta. We're using it in place of delta because we can't run gradient descent on delta. Okay, so we'll call this loss function L. Okay, and it's going to be decomposable. Let's call this we're going to do f of alpha. I'll use f as a function because we're going to run gradient descent. And it's going to be a loss function on g of alpha, number x and y, right? So this is going to be our loss function, which is not quite going to be this delta function, but we're going to see in ways which is close. Okay. Okay, and we're going to replace a little loss function over each of the points. So it's going to be decomposable, and I'm going to define this smaller loss function over just one xi and yi here, right? So I've taken my choice of alpha that defines my linear function and the data point x and y, and this will be the loss function, just L, right? Which will be simpler to find, and then I'll just add these terms up, right? So it's going to be decomposable, which will nice means if we can run gradient descent on this, we can also do we can also do batch or stochastic gradient descent. Okay, and we're going to use one more trick. It's going to be kind of an important thing to think about. The sum, instead of parameter having this g alpha xi yi inside there, we're going to kind of simplify this to be L of alpha times zi, okay? Where we're going to write zi is equal to yi g of alpha xi. Okay, we're going to do this clever, this kind of, I think this, when I first saw this, I thought this was pretty clever, and I'll explain why. This clever change of variables inside of here, and the zi will end up being a lot easier to think about what's going on. Okay, okay, and then this will end up being I equals 1, and we'll think of this as fi of alpha, right? Where again, fi of alpha is equal to this loss function of zi, which is equal to yi g of alpha of xi. Okay, and we're going to write it this way. The reason for writing it here like this, right? Because now, if I write like this as a function of alpha, I can run kind of SGD, right? I can run stochastic gradient descent on this. So eventually I want it's a sum of these decomposable terms, a function of alpha, and the terms for xi and yi go into the definition of fi, right? It's going to have all these little cost functions, and I'm going to add these things up, and kind of each one might not be full rank, but the combination of all of them are going to be full rank, kind of similar to how it was in the case of regression. Okay. Okay, so let's go back and look at this function this kind of cool trick here. Zi yi g of alpha xi. Let's think about what's going on here. Okay, this is this will allow us to really simplify what we're looking at here. And this allows us to treat the two cases of yi being positive or yi being negative kind of in a similar way, right? So if yi equals -1, right, then we want gi to be of xi. We want this to be small, right? Well, in fact, we want it to be less than 0. We want it to be negative, right? So, and if yi equals +1, then we want g of I xi to be large and in fact greater than 0, right? So this is what we wanted. We want the signs to match, so if gi, but if we look at here, this and these terms kind of cancel out. We're multiplying them by each other. So in general, we want zi to be greater than 0 in either case. Okay. If yi was negative, then we wanted g of xi to be negative. But then we want the product of them to be positive, right? Okay, so this kind of factors both of these things in. And if yi is +1 and we want gi to be positive, positive times positive is positive, right? So now we can kind of think about this cost function in the space of these zi's. Okay, so if we remember that zi is going to be yi g of alpha xi, and remember the g of alpha of xi is just going to be, it's just a dot product here, right? So then we're going to think about this function g of we think of this function delta as a function of z, right? And move this down a little bit, okay? And so this is going to be 0 if z is greater than 0, right? I classified it correctly. If I have this delta, if z is greater than 0, then that's great. And it's 1 if, this is maybe delta I on the ith point here, if zi, or this is, let's see, delta of zi on the ith point here, if this is less than 0, right? So I can have this delta function for a single point now, right? And I can think about drawing a picture here. Okay, and this is z, my z function, and there's this critical point at 0, right? So this is is a real value, right? So I've mapped, remember this is zi is yi g of alpha of xi, but now I can think about this as a single real value, and there's kind of this important step function x. Let me make this here in blue. Okay, so if zi is less than or equal than 0, I guess I can here. So if it's less than 0, I'll say that I get a value of 1, a cost of 1. If it's greater than 0, I get a cost of 0. That's great. So this is my counting function, right? This is counting, or this is for a particular point. Basically is answering, say, is xi, yi misclassified by g of alpha, right? That's what this is asking here. Okay, and now we can kind of see why this does not have a gradient, okay, in terms of alpha. Okay. So alpha is controlling z here. Remember, this is going to be equal to yi dot alpha comma xi, this dot product. Okay, so I'm doing yi times this guy, that y a little bit nicer. So yi times this, and it's a linear function. And so what it would allow me to do is the linear function allows this threshold, so to move back and forth, right? That's all it would allow it to be effectively with alpha. It changes for x whether kind of what my zi value is, right? So if I pick a particular value, let's say here, right? So if this is zi for one particular thing, well, if I change alpha a small amount here, I can move a little bit, but the cost function is still 0, right? And if I'm here, then I can move back and forth, but the cost function basically stays the same. And if I cross over that boundary, it's a discontinuity. There's not a derivative, a gradient defined there either. Okay, so I'm not really getting a gradient defined here. So I need to replace this with the function, and I want to make it so it's a convex function as well. If I don't have a convex function, I might create a bunch of local minimum and all these other sort of issues. Okay, so I want this, and I want to do a convex relaxation. Why is this not convex either? Well, because if I look between these two function values, it's going to kind of cross over this function here, right? If I look between this for this value or this value, well, it's going to cross over the function. The function needs to stay below that green line, right, for any pair of points here. And it's not staying below the green line, so it's not going to be convex when it goes across here either. So it's not even convex, so I'm not even going to have a bunch of local minimum, in fact, in this case. Okay, so what I'm going to want to do is replace this delta function on a single point, on a single zi, with a convex relaxation of it. That's going to kind of approximate what's going on here. Okay, so let me try and start with the hinge loss. Okay, so the hinge loss is going to be a proxy function, which we're going to say L is going to be equal to, or L of z is going to be equal to the max of 0 and 1 minus z. Okay, so this is going to be my proxy here. Okay, and so if I draw this function, let's see this again. So I've got my function, this is 0, this is for the value z, right? And there's this hinge loss, or sorry, this delta function, which looks like this. This is the delta function here. And this hinge loss is going to look, so it's going to be a maximum of 0, okay, but it's going to be 1 minus z. So as z gets bigger, so if z is equal to 2, let's look at this is z equals to 1, z is equal to 2. Okay, then 1 minus 2 is going to be -1, but I'm going to take a max, so it's going to be 0. And everything along here, in fact, anything past the point of z is equal to 1 is going to give a value 0, and then it's going to increase. So this is going to be the hinge loss. Okay, this is this convex relaxation of this. Okay, so what's happening here? if I classify something well, right, so I'm over in this region over here. This is well classified. Okay, so that means that if I remember this green line over here, and I have a normal function, and I have a point, and I have a data point x here, right? This here is a distance of 1. If I'm more than a distance 1 classified in the right direction, right? This is a positive point over here, then it's going to have a cost function of 0. Okay. If on the other hand, once I cross over, I'm within a distance of 1, right? If I move this a little bit closer, now it's going to have a cost function. It's going to have some penalty. Even though it's classified correctly, it's a little bit too close for comfort, I guess, right? And then as I get over here and I keep going this way with a positive point, it's going to get more and more penalty. That's bad, bad, bad. I'm getting further and further misclassified, right? So this would be equal to like a zi value of, say, -2, right, would be out here someplace. So a zi value of equals -2 is going to have a cost function up here of, so -3. Okay, if it's exactly on the boundary, it's still going to get a cost function of 1. That's too close to the boundary. I'd rather push it away from the boundary. Okay, and as I get, if it's worse and worse misclassified, it's going to be pushing even harder, right? The bigger the cost, the harder it pushes back. Okay, so this function is convex, right? If I draw this line between any 2 points, that green line is going to stay above the function. So it's going to be convex. That's going to be good. Okay, is it so differentiable? Well, it's going to have a gradient. The gradient of L over here is going to be equal to 0. Well, that's okay. Those points we've solved. Those are misclassified. We don't need to change those points. Those points are fine. So that turns out that's okay. And the gradient of L up here is going to kind of be pushing it back in that direction. The gradient over here is well defined, and it's basically just going to be over here. It's just going to be equal to -z, which is going to be yi of alpha. So if yi is negative, negative y is negative, it's going to be pushing the alphas to be bigger, and if it's positive, it's going to be pushing them in the other way, right? And that's going to be true here in this middle region as well. This middle region, kind of, it's still going to be pushing them away from the classifier. It's not differentiable right here. At this one point, it's not differentiable. So you have to have a little bit of a case statement here. It's a little bit annoying, and so it's not quite differentiable. But at that point, you usually just say the gradient is 0 if you fall exactly on that point, right? It's similar to this question earlier about what happens if your classifier is right on the boundary. Okay. Okay, so this is the hinge loss. This is probably one of the most popular loss functions people replace. They'll replace this counting of how many points I have with this function instead. How many misclassified points? This is actually the convex function that is kind of in some ways the closest approximation of this delta function. Okay, it's convex and it's close everywhere. You could change the slope a little bit depending on if you cared about points near the boundary or you care about them further away from the boundary to be closer. But this is the closest to the counting function you can do. Okay, and I can write this down as I can plug it into here, and I can write down this expression, and instead of doing the sum of squared errors and I get the least mean squares update rule, I can take the derivative here again. It's again going to be fairly simple to do once you write it out, and you can run your gradient descent algorithm as we did before, and this will solve for some parameters alpha, which will come up with a pretty good classifier. Okay. Okay, let me mention, these are not the only loss functions. I'll mention some other loss functions here. Okay, so we're going to start. Let's draw a couple of pictures with each one here. So this will be the delta function, and then there's a function called the smoothed hinge, which will start here. I'll start with the squared hinge loss. So the squared hinge loss, this is going to be L of z is equal to max of 0, 1 minus z squared. Okay, so this is kind of similar. A little bit more space here. Okay, so this is pretty similar, but I squared it instead. If I'm penalizing, I'm doing a squared penalty. And so what's going to happen now is that this point, so at this point, why is my is of L is so well defined, right? So my gradient is well defined at this point because remember the bottom of parabola, the gradient is 0, the same as right there. So the gradient is well defined everywhere now, and I'm getting something like sum of squared errors again. But the errors are increasing. So outlier points, misclassified points are having a much bigger penalty than I did before. And so it's more kind of susceptible to outlier points as opposed to the points closer to the boundary. Okay, so that's one approach. There's something kind of in between, right, where if I put my delta function here, this is going to be called the smooth hinge. Okay, and it's going to look fairly similar to here, and then it's going to be quadratic up to this point. Actually, usually they do, so it's quadratic up to here, and then it's going to be linear. So it's going to have 3 pieces here. So L of, so this one's going to be a bit more complicated. It's going to have 3 pieces. It's going to be 0 if z is greater or equal to 1. Okay, right, that's the part that's out here. Okay, it's going to be 1 minus z squared divided by 2 if let's say if z is between 0 is in 0 and 1. And so that's going to be the part, say this is going to be in here. That's the quadratic function divided by 2. This is just the most common way to do it. You can change that 1 over 2 if you want. And this can be 1/2 minus z if z is going to be less than 0. So the reason for doing this is that this part here, right, is going to kind of look like the hinge loss. It's just a linear function growing at a linear rate. right? So if it's less than 0, I'm still getting the same linear cost. There's a 1/2 in front. That doesn't matter so much. It's not a strict upper bound of the delta function. If that matters, I could shift it, shift stuff, some constants someplace. But this has a gradient defined everywhere, which is nice. It's convex, which is nice, and it grows linear as I get further and further loss. Right. So I combine both the kind of the both good parts of the squared hinge and the hinge loss, but now it has 3 components to it, which is maybe kind of annoying. Okay. Okay, so let me add one more common function. Okay, and this is probably one of the most used functions. So again, my delta function is here. Okay, so let me first, before I introduce the delta function, I'm going to say a function called this is called the ReLU, the rectified linear unit, which comes up a lot. This is common in deep learning. Oh, can you rewrite the second equation? Yeah, this one, the second equation, the smooth hinge loss. Let me rewrite this here. This is 1 minus z squared divided by 2 if z is in 0, 1. And this corresponded with this green line. Okay, great. So this is the ReLU function. The ReLU function comes up a lot in deep learning. This turns out to be a common activation function, which is kind of like a loss function. It's a little bit different, but it's a shifted hinge loss. So now it's not an upper bound of the delta function, but I've just kind of shifted the hinge loss. Here, this one is max of 0 and minus z. Okay, so that's very similar. And now we're going to do a convex approximation of this ReLU. Let's say the kind of a simple smooth approximation of the ReLU. That's going to look something like this. Okay, kind of a little bit hard to draw. This is going to be called the logistic loss. Okay, and this is in L of z is equal to, this is the natural log of 1 plus x, that's e to some power of minus z. Okay, so the x is kind of an approximation of the ReLU. It's always going to be above the ReLU cost function, and it's going to be smooth. And turns out the gradient of this is going to be smooth and easy to compute everywhere. And if I solve with gradient descent, if I solve the logistic loss with gradient descent, then this is called logistic regression. Okay, so logistic regression is kind of a very common, simple way to find a linear classifier. It gives you a linear classifier. And you set it up kind of like and it's going to be just like for homework 4, where you solve the actual regression problem for the sum of squared errors. Well, if I plugged in this loss function instead, and I took its gradient, and it turns out it's got an easy to find gradient everywhere, then I can do stochastic gradient descent or batch gradient descent, and the output is going to be something that's going to do well for the classification problem, where my yi's are the -1s or +1s instead of a real value I'm trying to predict. And this is one of the most common ways to solve for a linear classifier. Okay, and it's trying to approximate, again, this delta function. And so I kind of took that formulation. So if you put these back together again, I'm going to try and take this formulation where I've taken this cost function, and I want to count the number of misclassified points. And I've rewritten the misclassified points by the z function, right, which multiplies by the sign I want times the output of this linear function. This is going to be a dot product, right? So it gives me this delta function as a function of z, which is a function of alpha, again, for any of the data points, right? And I can't optimize this function, so I'm going to approximate it with a smooth convex function. And there's the loss, there's the hinge loss, which is kind of the simplest thing, or there are these other variants, and the logistic loss function, right, is this guy here, this logistic loss function. If I plug that one in, then and I solve for alpha using this, then remember alpha is tucked inside of that z, right? Then if I solve for alpha for the sum of these with stochastic gradient descent or batch gradient descent, that's logistic regression. It's going to go back and give me this linear classifier here, this green one here. Okay, so we're out of time for today. We're going to go back and review this. I know I kind of went through a lot of stuff here, but we already got to kind of logistic regression, which is a core algorithm. And we're going to come back and see kind of a different, more common, still iterative, but more combinatorial take on this algorithm here. Okay, and so hopefully this is starting to make sense. But if you got lost in the notation, I'll try and review that again at the beginning of the next lecture.